The line 2x plus 4 intersects the y-axis at r, as shown. A second line parallel to the y-axis is drawn through P0, with p greater than 0. These two lines intersect at Q. Determine the length of OR. Well, OR, I guess, is this segment right there. So I guess we just have to figure out what is the coordinates of R. R is on that line, y equals 2x plus 4. So y is equal to 2x plus 4. And then R happens on the y-axis. So that basically means when x is 0. So when x is 0, y is 4. So that means the coordinates of R are 0 and 4. So the distance from the origin to R would be 4. So I guess OR is equal to 4. Determine the coordinates of point Q in terms of P. Q in terms of P, okay? Well, the same equation, we're trying to find the coordinates. So the x-coordinate is the same as the x-coordinate of Q is the same as the x-coordinate of P, which is those letter P, lowercase. So that's going to be just P right there. And then to find the y-coordinate, you just sub that into the formula, so it'd be 2p plus 4. So P and 2p plus 4 would be the coordinates of Q. Part C. If P is 8, determine the area of OPQR. OPQR. So let me just draw a parallel line there. So this, from here to here is 4. From here to here is P. But they're telling me that P is 8, so that's 8. And then from here to here is 8. And then from this point to Q, well, Q, the y-coordinate is 2p plus 4, and P is 8. So y would be 2 times 8 plus 4, which is 20. But we got to subtract that part to just get this part, so that's going to be 16. Okay, so that would be 4 times 8 plus 1/2 base times height, 1/2 8 times 16. And that's 32 plus 64, and that is 96. Part D, if the area of OPQR is 77, determine the value of P. Okay, so very similar, but this time kind of working backwards, I guess. So instead of the values that I put in, this is still going to be 4, but this is now going to be P from here to here. And then, of course, from there to there is also P. And then from here to here would be 2p plus 4 minus 4, which is just 2p. Okay, so that means this would be 4 times p plus 1/2 p times 2p, I believe. And that they're telling me is 77. So 4p is plus p squared, I believe. So let's see, this is going to be p squared plus 4p minus 77. And I'm pretty sure that factors pretty nicely. P711 plus minus, I believe. Okay, so since p has to be a positive number, because it tells you that in the question, p is equal to 7. If f at x is equal to x over x minus 1 for x not equal to 1, determine all real numbers are not equal to 1 for which f at r is r. Okay, so f at r, we want it equal to r. Well, f at r would be r over r minus 1. And I think that's it. That's the algebra. So let's solve this. Cross multiply, and you will get r squared minus r is equal to r. And therefore, r squared minus 2r is 0. Factor out the r, and you get r and r minus 2. And therefore, r would be equal to either 0 or 2. Part B, if f at x is equal to x over x minus 1, and f at x is x. Show that f at x equals x for all real numbers. Okay, so same sort of story here. We want to show that f at x is equal to x. Okay, so let's see here. Are we using the same formula? Yeah, it's the same formula. Okay, so let's do this carefully here. So this is going to be f at x over x minus 1. Actually, let me start off with left side. So left side equals. And then eventually, hopefully, the answer will be x, which is the right side on that guy. So this is going to be, I got to sub it in again, right? So x over x minus 1 all over x minus 1 all minus 1. Yes. Okay, so we got to get a common denominator, that kind of story. X over x minus 1. And then we have x minus x plus 1 all over x minus 1. So x over x minus 1, and this looks 1 over x minus 1. So this is x over x minus 1, invert and multiply. And we have x, which is right side. So there we go. We just proved left side equals right side, and therefore that statement is true. Suppose that x is a real number. Define g at x is 2x over x plus k. And determine all real values of k for which g at x is equal to x for every real number x, with x not equal to negative k and g at x not equal to negative k. We begin with what they gave us, which is g at x is equal to 2x over x plus k. And g at x is x. So, what are we trying to figure out here? To have all real values of k. Okay. All right, so let's plug this in and off we go. So this is going to be g at 2x over x plus k. And then we got to substitute this into this guy. So done carefully, that will be 2x over x plus k. That takes care of the numerator. And then 2x over x plus k is equal to x. So I think hopefully I've done that correctly. Okay, let's move forward. So the top is going to be 4x over x plus k. And the bottom, we're going to have to multiply x plus k like that. So it's going to be 2x plus kx plus k squared all over x plus k. And then when you invert and multiply, these x plus k's go, and you guys know how to do that, so I'll just skip that. I'll just do it in one step. So it just becomes 4x over 2x plus kx plus, oops, let me stick that in there, plus k squared is equal to x. Okay. At this point, what are we going to do here? Cross multiply, perhaps? So this will be 4x is equal to 2x squared plus kx squared plus k squared x. Anything we can do here? I'm trying to see here, what can we do? Let's put everything on one side. And then let's see if we can collect like terms. X squared k plus 2 plus k squared x minus 4x, correct? So x squared k plus 2, I think I can factor out an x, and I think that's it. K squared minus 4. I see. Well, I think I have a little bit of help, not a lot, but a little bit. With that, k squared minus 4 is k minus 2, k plus 2. So then finally, I think I can do k plus 2 from everything, and then you have x squared plus x times k minus 2. And I think that's as far as I can go. So that means that k is equal to minus 2. And this is true for all values of x. Suppose that a, b, and c are non-zero real numbers. Define h at x to be ax plus b or bx plus c for x not equal to minus c over b. Determine all triples, a, b, c, for which h at x equals x for every real number x. Very similar, I think, just a whole bunch of letters this time, so this is not going to be fun. But here we go. Let's make sure we don't make any mistakes here, because we got a whole bunch of letters, so it's kind of, I don't know, abstract perhaps. All right, so let's start with what they give me. h at x is x. All right, so that's going to be h at ax plus b over bx plus c is equal to x. And then we have to now substitute this into the big long equation. So it's going to be a over ax plus b over bx plus c, and plus that b over b times ax plus b over bx plus c, and plus that c. So there we go. Okay, so far so good. And then a whole bunch of we got to add these fractions. So that's going to be ax plus b times bx plus c all over bx plus c. And then the denominator, the bottom guy, that's going to be a times ax plus b plus c times bx plus c all over bx plus c. So as before, if you invert and multiply, these bx plus c's will disappear. So I will just skip that step and just write the just what's the remaining, bx plus c all over a over ax plus b plus c bx plus c, like that, and that equals x. At this point, I will cross multiply, and that's going to be a. Let me cross multiply, and also let me just expand and just save some time here. And hold on. Yeah, and then I'm going to collect like terms while I'm doing it too. But you guys can follow what I'm doing. So the goal is eventually to try to get this factored, very similar to what I did last time, but this time, of course, it's a little bit more complicated since it's all letters. But I think I can. See, I already got a little bit of factorization going there. And not sure what I can do here. So let me just leave that. And then I got an x squared here. AB plus BC. And I think I can factor out, what can I factor? An x. B squared plus C squared. Let's see here. Should I put everything on one side? Yeah, I think so. And if I put everything on one side and factor further, I'll have a plus c x squared, and then I'll have c squared minus a squared, and then I can have another factor. Okay, so this actually looks like a quadratic to me. I got something x squared, something x, and then that. And this will be indeed equal to 0. It's true if the coefficients are 0. So those coefficients would be this guy, and this guy. Okay, so let's work with that and see what we find. So b plus a plus c, we want that to be 0. And the only way that is true, well, I think they give us some parameters, right? B is in the denominator, so it cannot be 0. It's in the denominator for h at x also, because that would make it undefined, because we're talking about real numbers, right? Yeah, real numbers. Oh, there you go. It even tells you non-zero. Non-zero. So b cannot be 0. So that means the only choice is that a has to be equal to negative c. That's a very important point. And then the other coefficient, that guy, c squared minus a squared is 0. So that means that, again, when you do that, a would be either equal to c or equal to minus c. And let me go back. Are they different? A, B, and C are non-zero real numbers. It doesn't tell me that they're different. Okay, well, well, let's just go with this. Continue with this. I'm just trying to think. Well, we want it to be consistent, so I guess we are consistent. We got two of the same findings. Yeah. Okay, and then the next guy, this one, is it the same thing? Yeah, it's the exact same thing. Okay, so that basically means that a is equal to minus c. So we got a equals minus c in all three. So that means my triple would be any triple of the form a, b, and minus a, because c is equal to minus a, where a and b are non-zero. Given a sequence a1, a2, a3, dot, 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 of positive integers, we define a new sequence b1, b2, b3 by b1 is equal to a1, and for every positive integer n greater than or equal to 1, bn plus 1 is bn plus an plus 1 if bn is less than or equal to an plus 1, or bn plus 1 is equal to bn minus an plus 1 if bn is greater than an plus 1. For example, when a1, a2, a3 is the sequence 1, 2, 1, 2, 1, 2, and so on, we have n, an, and bn as follows. Suppose that an is equal to n squared. For all n greater than or equal to 1, determine the value of b10. All right, so they are applying this to get values of the b's. Now, it might seem a bit difficult, but I'm going to walk you through it, and then after a while, you'll become an expert, I think. So let's start with this guy. So very similar to what they did, let's make a table. So we got n, we have an, and we have bn. Now they're telling me that all the an, well, let me just put in the values of n. We'll go up to 10 since they want b10. 4, 5, 6, 7, 8, 9, 10. And therefore an is equal to n squared. So this is 1 squared, which is 1, 2 squared, 4, 3 squared, 9, and so on. 16, 25, 36, 49, 64, 81, and 100. So you guys understood so far, right? Okay, so now we got to figure out the bn's. So the first few, I'll calculate them, and then you'll kind of get an idea of how I'm actually doing it. And then once you get an idea of how to do it, you can kind of just do it really quickly. Okay, so the first one, b1, well, b1 is equal to a1. And that's actually in the question right here. b1 is equal to a1. So that one is easy. So that's just going to be 1. Okay, now we got to do b2. So b2, what you do first is you got to look at a comparison between, in this case, b2 and a3. Or actually, no, you would be actually looking at a comparison between b1 and a2. So here's b1 and here's a2. And you have to see which one is bigger. So obviously a2 is bigger. So it would be this scenario, the first scenario, right? Because a2 is bigger than b1. So if that's the case, then you just add those two numbers. So 4 plus 1 is 5. All right, so let me walk you through a few more. Again, now we got to figure out b3. To figure out b3, we have to compare b2 and a3. So we got to compare b2 and a3. And which one is bigger? Well, in this case, a3. So again, it's this scenario. So we got to add them. So 5 plus 9 is 14. Are you getting the hang of it? So compare this one and this one again. Which one is bigger? This one. So it's the first scenario. So you add them. Now again, you compare this one and this one. This time, this is bigger, so it's the second scenario. So if it's a second scenario, you subtract them. So it would be 30 minus 25, which is 5. Got it? So then now again, compare this one and this one. This one is bigger, so you'd add them, 41. This one and this one is bigger, so you add them, 90. This one and this one is bigger this time, so you subtract them, so it'd be 90 minus 64, 26. This one and this is bigger, so you'd add them, so it'd be 107. And then finally that one and that one are compared, and that's bigger, so you subtract them to get 7. And 7 is B10. And that is the answer to this question. Suppose that an is equal to n for all n greater than or equal to 1. Determine all positive integers n with n less than 2015 for which bn is equal to 1. So same type of story here. We've got to make a list n, an, bn, and we've got to go and try to figure this out. So this time we are trying to find any time that bn is equal to 1. And then we actually have to find all the values of n for which bn is 1. So my hope is sooner or later we will come to a pattern, and hopefully that pattern will come sooner rather than later, and we'll see what happens. So an is equal to n, so that's makes our life a little easier. That's just going to be 1, 2, 3, 4, 5, 6, 7, like that. Okay, so how are we figuring out bn again? It's the same. It's the same thing up here. Okay. So if it's the same, I guess I can do it pretty quickly, I hope. So this is 1, and then you just compare that with that. So that's going to be 3. Compare this. This is an equal situation. If it's equal, it's the first one. If it's equal, it's the first one, and you add them. And we didn't encounter an equal so far. So that's 6. Compare that and that. And this one is bigger. So that's 2. And so on. I mean, you guys can figure this out. I don't need to walk you through it again. So I'll just fill it out. Okay, so I got bn equal to 1 when n is 6. See, right here? Okay, so let's keep going. And like I said, you can do this. I don't need to walk you through it. I think by now you should be experts on how to figure out the bn's. So we got 8, 16, 7, 17. Okay, so we got to keep going here. N, an, bn, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, what am I doing here? These are actually teens, and this should be a 20. Okay, so, and this is of course the same. So let's go through this. Okay, bn for this row would be, let's see here. We got to compare that one and that one. I got 17. And then we got to compare that one and that one. So that's going to make it 6, I believe. Yeah, and then 18, 5, 19, 4 for n is 15, 20, 3, hold on, 3, 21, 2, 22. Okay, so far we only have just this guy that's a 1, and then 1 when n equals 6. Huh. Oh boy, I guess they're making us work here. So let's just keep going here. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And these are all the same. Oops, put that there. Hold on, what am I doing here? 28, 29, 30. Okay, so Bn, so what do we got to compare here? We got to compare that and that. That's how I got 22, that and this now. So it'd be 1. Oh, 1. Oh, okay. Finally, I got a 1. That happens at 21. Let's see what will happen later. 23, 46, and it just keeps on going. Okay. Let me see what I can do so far instead of keep going here. Because I got to extrapolate. Bn is equal to 1, correct? And then the next one was 6. So Bn is equal to 1 when n equals 1. So B1 is 1. And then B6 was 1. And then B21 was 1. Okay. I'm trying to see what kind of pattern is this? 3 and plus 3. I really wish I had one more. And let me keep going here, and then I'll come back to you guys. Let me just do it on my own instead of walking you through it, because that's going to be painful. So let me figure out a couple more, and I'll come back. So I went up to 66, and I got one more. And then I couldn't get any, and I'm sure there's more, but I couldn't find any for a long time. So I think I'm going to be forced to kind of come up with a pattern from these. And I think I can. And I think it is, I think it's 3n plus 3. So for example, for n greater than 1. So for example, when n equals 1, it's B1, right? And that's 1. When n equals, hold on, what am I doing here? No, that's right, that's right. When n equals, and then you can just extrapolate. So then when n equals 1, you have to put it in there. And that would be 3 times 1 plus 3, which is 6. And that's the next one, B6. And that's also 1. So we got that guy with that guy. And then we take this 6 and plug it into this formula. So it would be 3 times 6 plus 3, which is 21. And there you go. So B21 is 1. And then we would do it again. The next one would be 3 times 21 plus 3, which I believe is 66. And there we go. B66 is 1. So let's keep going here. The next one would be 3 times 66 plus 3. 3 times 66 plus 3 is 201. So B201 would be 1. The next one would be 3 times 201 plus 3, which I believe is 606. So that means B606 would be 1. And then the next one would be 3 times 606 plus 3, which is 1821. Yeah, 1821. And then I think that's it, because there's a limit, right? Yeah, n has to be less than 2005. So I think that's it. So what is the question asking? Determine all positive integers n. Okay, so all positive integers n would be n equals 1, 6, 21, 66, 201, 606, and 1821. So 1, 6, 21, 66, 201, 606, and 1821, for which Bn is equal to